Hello, so in this lab we will be doing the interpretation of ray diagrams and convex lenses. So the first thing you need to know while you draw the ray diagrams is the Snell's law. Snell's law describes the relationship between the angle of incident and the angle of refraction. As you can see in this picture, when light ray goes from one medium to the other medium, it bends towards or away from the normal. And uh, and the Snell's law can be stated as n1 sine theta 1 equals to n2 sine theta 2, where n1 is the index of refraction of the first medium, n2 is the index of refraction of the second medium, and theta 1 is the angle of incident and theta 2 is the angle of refraction. In this slide, we can see how the light ray bends towards or away from the normal. In the first picture, we can see that the light ray comes from a lower index of refraction medium to a higher index of refraction medium. Therefore, light ray bends towards the normal. It's like the light ray comes from air to the water. And in the second picture, we can see the light ray goes from higher index of refraction medium to a lower index of refraction medium. Therefore, the light ray bends away from the normal. It's like the light ray goes from water to the air. Then we will be talking about the lenses. A lens is an object that is designed to refract light in a specific way. We are specifically interested in two basic types of lenses. Those are convex lenses and concave lenses. As you can see in these two pictures, concave lenses are thinner at the center than at the edges, while convex lenses are thinner from the edges. And you can see that convex lenses converge the light which goes through it, while the concave lenses diverge the light which goes through it. And in these ray diagrams, you can see that convex lenses have a positive focal length, while the concave lens have a negative focal length. In this lab, we will be focusing about convex lenses. Convex lenses bring the rays of light that passes through the lens closer together. Therefore, it is called as a converging lens. Then you can see the optical center. Optical center is the center point of the lens itself. The ray of light which passes through the optical center goes straight and does not deviate. Then you can see the principal axis. It's the line which passes straight through the optical center. In here, we can see the focal point or the principal focus. It is the point on the principal axis of the convex lens where all the light rays parallel to the principal axis converge after passing through the lens. If the light rays are coming from left-hand side of the lens, they will converge at right-hand side of the lens and vice versa. Focal length is the distance between the optical center and the focal point, and focal length depends on the refractive index of the glass which is used to make the convex lens. As I said, focal length of the lens depends on the refractive index of the glass and its curvature. In case of higher refractive index, focal length will be short. Similarly, if the curvature of the lens is more, then also the focal length will be short. When we draw ray diagrams for a convex lens, we need to know three principal rays. In here, the first principal ray has been given. We can see the light ray which goes through the optical center of a convex lens goes straight, and also a ray of light going along the path of a principal axis of a convex lens also goes straight and does not deviate. The second principal ray is the ray which goes parallel to the principal axis. After refracting from the convex lens, it will pass through the focal point of the convex lens. The third principal ray is the one when the light ray passes through the focus of the convex lens, then it becomes parallel to the principal axis after the refraction through the lens. In here, we have given some examples of how the image will be formed through a convex lens. The type of image formed by a convex lens depends on the position of the image. As you can see in this first example, the object is placed between the center and the focal point of the convex lens. And you can see the image will be formed in the same side, but it's a virtual image and it's upright and it is magnified. In the second example, the object has been placed at the focal point of the convex lens, and you can see the ray paths become parallel to each other. Therefore, the image will be formed at infinity, and you will be able to get a real image, which is inverted and enlarged. And in the third example, the object has been placed in between the focal point and twice the focal length. Then the image will be a real image, and you can see it has been inverted and magnified. In the example 4, we have placed the object at a distance equal to twice the focal length, and you can see the image will be formed at a distance equal to twice the focal length, and the image will be the same size as the object, and it will be real and inverted. And in the example 5, we assume that our object is at infinity, and the light rays will be converged at the focal point and will give us a real image. And you can see this image is inverted and reduced in size. In the previous 5 examples, we showed you how you can get the image location using 2 or more principal rays. Now you should be able to get the image location of any object which is placed in the principal axis. And in this example, we show you how you can get the image location of an object by using 2 convex lenses. What you have to do here is just get the image location through one convex lens and then take that image as the object to the second convex lens. And you just have to draw great parts of these 2 images. Magnification produced by the lens can be taken from dividing height of the image by the height of the object or dividing the image distance by object distance. That's the end of the presentation. Thank you for watching.